So do you have any kind of requests? Okay. So that's like a little bit difficult because so I guess like what we can do is because like it would essentially be kind of like redoing the lecture. So I guess one thing that we can do that's different is looking at specifically the slides that are like what do you need to know? And then kind of as we go through them, you can like ask questions and maybe we'll go back to yeah. So I'll just go and find the okay. So this is the first kind of what do you need to know thing, right? And that's one nearest neighbor and basically what it does, right? So the setting this is the general setting for kind of what's called supervised learning, right? So you have a training set. So the training set would be, pairs of X, Y, where X is the input and Y is the intended output, right? And then, so this is essentially kind of questions X to which you know the answers, right? So Y would be the answers, right? And then you want to somehow use this training set in order to answer what is the corresponding Y to a new X. And this is kind of very abstract, right? So those could be anything. So specifically with the image examples, the X's would be images, and then the Y's would be the labels of the images. So for example, the names of the people in the photo, right? So, okay, so that's the setting. So now the nearest neighbor algorithm, one nearest neighbor algorithm is like this, right? So you have pairs X, Y, where X, let's say, is the image, Y, let's say, is the name. And then the algorithm is if you have a new input X, so this represents the new input, we can say, okay, like we'll compare the new input to every X in the training set. So we'll compare X to X1 and we'll compare X to X2. And you can do it like this, or you can kind of picture it comparing X to this one, comparing X to this one, and so on. We'll find the Xi in the training set that's the most like the input X. So let's say X2 is the most like the new input X, and then we'll output the corresponding Y. So for this new input X, because it's the most like X2, for example, we'll output Y2. Right. So there's various ways of comparing essentially vectors, right? And one way is to compute the cosine of the angle between the vectors, for example, and to say, x0 and x1 are the most similar if the cosine of the angle between them is as large as possible, meaning the angle between them is as small as possible. Right. So that's like the formula for cosine. So what we said is like you could also just say, I'll compute the Euclidean distance between the two vectors, right? So that's another possible way to say whether it's similar, and then the smaller the Euclidean distance, the more similar they are, right? So another thing, and that is something that we've seen later in the lecture, is you can just compute the dot product and say, the larger the dot product is, or the absolute value of the dot product, the more similar in the inputs. And the intuition is just that, like if the absolute values of the vectors are approximately 1 anyway, we can just look at the numerator and kind of ignore the denominator. So the need to know here is basically, like if you have an input X and you have those guys, they're, implemented somehow. So it depends on how they're implemented, of course. Then what you do is you just do a for loop where you compare the input x to x1 and x2 and x3. You find the xi such that the xi is the most similar to x, maybe, for example, in a sense of Euclidean distance, or in the sense of cosine similarity, or in any other sense. And then you output, like if the answer is xi is the most similar to x, then you output yi. Does that make sense? No? Oh, okay. Yeah. Okay. Yeah. Okay. All right. Okay. So okay. Yeah, so that's that one. Okay. So the next need to know is the computation for kind of the shallowest possible neural network, right? So yeah, so this is shallow as opposed to deep, so no hidden layers, right? So here, essentially, the point of the slide is that this graph represents this formula. Like this graph is a way to kind of say what the formula is. And what it is, the sum for W. So the J here changes, the J here changes. So it's like W1JK times XJ for every possible J, sum all of them up. And here it's represented as when you're computing Z1, you're doing x1 times this weight plus x20 times this weight plus x4000 times this weight. And that all goes to Z, right? So this is just a picture, essentially, that represents this formula. So B is another set of numbers, right? So when you're computing Z1, it's like this sum plus the B that corresponds. So this is like B11. For Z1, it's B11. For Z2, it's B12, and so on. All right. So that's all there is. So it's like so this just represents, this formula. Okay. So in terms of need to know, like anything like that, right? So like if you have a picture like that, then, in principle, like instead of like writing it in algebra, you could write it in Python, right? So that would be, a nested loop where I suppose or like there's multiple ways of implementing it, but like the simplest possible thing is a nested loop where you compute Z1 using a loop that computes this, and you compute Z2 using, again, another loop, and so on. Right? No, so like so the formula for sigma I did not give here. So in order to implement it, like either I would say, well, like here's the function sigma, and you can call it, not even going to say what it is, or I'd have to give it, right? Okay. So this is that. Okay. So the next one is the face template stuff. So one way to look at this is you can say, okay, so like let's say that this network works. So what we mean by this network works is that when you plug in a new face X into here, then if it's the face of person 1, then most of the time Z1 would be high and the other Zs would be low. And if it's the face of person 6, then most of the time Z6 would be high and the others would be low, right? And then we can ask, okay, like, how do we like, so like, let's say we just found the weights and biases that actually produce that result, right? Like we came up with a formula that outputs what we wanted most of the time. So now we want to go back and say, like, how could that happen? So one way to try to explain it is to say, okay, well, like actually when you're computing Z1, what you're doing is you're computing this dot product, right? You're computing the W's that connect all the x's to Z1 dot x, right? So that's like part of the formula over here, right? So like this is a dot product, right? And then we say, okay, so Z1 would be high if the dot product of x and the corresponding w's is high. And then Z3 would be high if the dot product of x and the corresponding w's that connect the x to Z3 is high, and so on, right? So then you can say, okay, well, like thinking back to what we just said, you can think about the dot product as a rough measure of whether two vectors point in the same direction, right? So if the dot product is high, then if the vectors are roughly the same size, that means that the cosine of the angle between the vectors is high, meaning the angle is low or close to zero, right? So that's a measure of similarity. So then we can say, okay, like one way to interpret this is to just say, okay, like we have, you know, those six sets of weights. So like W1 everything 1 and W1 everything 2 and so on. And we're comparing those sets of weights to x by computing a dot product with them. So we can think of them as kind of templates for the different outputs. Because, so in this visualization, if x, so you kind of rearrange x, so x here is like flat, so this is like 64 by 64, but just flattened, right? So if you rearrange that into a vector and you dot product it, then it would be high just empirically because it was made to be so, that if this dot product is high, then it's Baldwin. And then if the dot product between x and this is high, then it's Carrel, and so on. So we can kind of interpret those as templates for the different people in the training set, right? And then like if you display them back again as images, you can kind of see that they look like faces, although kind of not very much. So going back to kind of need to know, so if you have a W, so the W would be, like, for example, like a matrix, right? Then, you know, if you want to extract and display the image, okay, like to extract it, again, kind of, there's various ways, like in MATLAB, you saw like the column thing maybe. So, but like you could just do a for loop, right? So like you need the vector where it's like W101, W111, W121, and so on. That's a vector. You can extract it. And then you need to depend. So this is implementation dependent, but if you want to display it as an image, you need to rearrange it so that, you know, like instead of it being one long vector, you just take, you know, like first line, second line, third line, and so on.
And so instead of a long vector,
right. You just rearrange it into like you pretend that it was an image. It was just like, you know, first row, second row, third row, all in a row. Yeah. All right. So that's like this. Okay. So yeah. So the next need to know is looking at a deep neural network and asking what is the job of every particular neuron, right? So what we mean by the job of every particular neuron can be kind of a little bit vague. So the way it was described in the lecture is we're saying, okay, like if we want to ask like what is this? So first of all, what's the computation here? The computation here is you plug in the x here, and then you compute this, and then from this you compute this, and then from this you compute this, and then you compute this, right? So you might like to ask, like what's, why have this neuron? Like, what is it doing? Because we had kind of an answer for the shallow neural network. The answer was, well, we can think of it as like matching different templates to the input, right? So here we can ask, okay, like if I plug, so in order to figure out like what this neuron is doing, I'm just going to say, so a unit, I'm going to say, I'm just going to look for all the possible inputs and look for the inputs that make it so that the value here is as high as possible, right? And that would give me an indication of kind of the job of this neuron, because I'm going to see which inputs actually make it so that the value is high, right? Mm-hmm. So, for example, like for any neuron, yeah. So, like apart from like the output neuron, where you kind of know what the job is, because like the job is to be high when it's image of type 1, and the job of this is to be high when the input is image of type 2, and so on. Right? Okay. So that was kind of the strategy. And then like here we've shown, okay, so like there is a neuron where, the images in the training set that make it so that it's as high as possible are like over here. And then there is another one that's where the images that activated the most are like this, and so on, right? So that was kind of the answer of how the visualizations are produced, right? So we plug in every input from the training set usually, and we find the images that activate the neuron the most. So if you have a function that computes the hidden neurons, so like you plug in the input and you get the values of the hidden neurons, you want to be able to find the images that activate the hidden neuron the most. Again, like this is like nothing. It's just like if you have a list of possible inputs, well, you can find the inputs such that f of x is as high as possible. Okay. Okay. So when modeling language, right? So you don't necessarily, so when we were doing kind of the face recognition example, we had sample inputs and sample outputs, right? So when you're modeling language, then all you have is just, strings of text. You don't really have, they're not necessarily at least separated into a question and answer, right? So what do we do? So what we do is like we basically say, okay, like the thing that we're trying to predict is what is the word that's going to come next, right? So if you have the input words like W1 to W3, and the next one is W4, you want to be able to predict it. So we kind of build this training set where the inputs are all the words that precede the next one, and then the output is the next one. And then we do the same with one more word, and the same with one more word, and so on. Okay. Say it. So it's just that like we're saying like we want the so we just like keep doing this, right? So like if this is if our sequence is like W1 through W6, I'm saying I want to be able to predict W4 when the input is 1, 2, 3. And I want to predict W5 when the input is 1, 2, 3, 4, and so on. So like for every next word, we just pretend that we don't know it and we try to predict it, right? And the way we kind of formulate it is the same as with the faces, right? So we just list all the possible words that we could have. And then when we look at the output of the network, we're saying if I want to predict that it's word number, so word number 3 in the vocabulary, then I want the output to be as close as possible to this, where it's all zeros, except that word number 3, except that output number 3 is as close as possible to 1, right? So it's the same as the face recognition task, except we kind of just take a bunch of text with no labels. It's just the text. And then we construct it as we are predicting the next word from everything that came before it. Does that make sense? Okay. So right. Yeah, so that's, and I think that was the last one. Yeah, I don't think there was anything. Yeah, there wasn't anything here that was like need to know. Yeah. Say. Oh, other requests or questions? No. Okay. Okay. So the task here is to take in a C string and to reverse it into reverse it like a word by word, right? Okay. So what we'll do is I'll just create a new string here. So that would be just the length of the original string plus 1 for the null. So now what I want to do is I want to separate them. Out by spaces, and then I want to write them in reverse order, right? So multiple ways of doing it, I suppose. So I guess what I'll do is I'll start from the end, and then I'll go character by character to the left until I encounter a space. And then once I encounter a space, I'll say, okay, extract this word and write it to res, right? So let me so res end would be like the index where I'm currently writing to res. And we'll have a str end, and that initially would be strlen -1. And that would be the index where currently reading at from STR. And I'm reading from the end, right? So now the loop would be go left in STR until I find space, and then read forward. And I'll keep doing it while STR end is not -1. If it's -1, that means that I'm done, right? So, okay. So I'm reading forward. Sorry, so I'm reading yes, I'm reading back, right? So I'm gonna say, so while STR end is greater or equal than 0, and also it's not a space. So STR at STR end is not a space. Subtract 1 from STR end, right? Okay, so that gets me to the point of now STR at STR end is a space, or STR end is -1. So now what I'll do is I'll go forward and I'll copy from this location to to res, right? So I'll start at strn plus 1. I. Okay, so while I is smaller than str length, str, and also it's not a space. And here I'll increment strn, and I'll increment I. Make sense?
So while it's not a space.
So I'm basically saying, so like the first one, so like str, and res initially it's nothing, right? And then I'm saying, okay, so we're starting from here, and then str end is here. Okay, str end is now here. And then for I equals this and I equals this, copy H and copy I into res, right? And now I becomes strlen str, so we're done. Okay. All right. So here there's two situations. So either res is either we wrote the last word, or we need to add a space, right? So if we still have, so if there is still stuff to write, so that means that if strnd is greater or equal to 0, greater or equal, yeah, we'll write a space. So after the loop is done, we need to add a null at the end of res. No, actually the opposite, right? So we need to return it. So you would free it after you've used it. Right? Because here the function returns a car star. So like after you've used it, printed it, or like read it or something that you can free it. But like if you free it before that, then the whole exercise would be pointless. Yeah. Mm-hmm. So okay. So first of all, the goal for a star is to find the shortest, so to find the shortest path possibly more quickly than Dijkstra would. And the way to think about it is as a modification of Dijkstra, right? So Dijkstra's algorithm, one way to do it. So one way to do it is to say we have a priority queue of nodes to explore. The way it works is we start with the source, so source gets explored first, and then any node that is explored, its neighbors get added to the priority queue to be explored next. So with Dijkstra, the priority is just the path from the source through the node that was just added to the node that's possibly to be explored. So when U gets explored, and you start with S, V would get added to the priority queue, with the priority being the shortest path from S to U plus the edge from U to V, right? And the idea with Dijkstra there is that, and that was kind of proven, it's not like super easy to prove, but it was proven that if you explore nodes in this order, so if you get the new node to explore from the priority queue such that the priority is as low as possible, then that priority is actually the shortest path from the source to this new node, and then like you explore it, you add its neighbors. Okay, so that was the point of Dijkstra, is that if you explore in that order, then you know what the shortest path is. But that doesn't guarantee that you would find the shortest path to a particular destination soon, particularly quickly, because the order in which you explore the nodes is strictly about what would allow you to compute the shortest path distance, right? So like the priority is like a convenience for determining the shortest path, right? So a star, you can think of it as a modification of Dijkstra, where what you're doing is you're prioritizing the explorations of nodes, not just by what would let you for sure definitely already know what the shortest path is, but also by whether the node seems like it might be closer to your destination. So if your goal is to just quickly find a short path to the destination, under some conditions, it would be the shortest, but like a short path. What you could do is you could just like prioritize the estimated path, length of the path from S to the destination, right? So of course, if you knew that, then there would be no question. You already know the shortest path, right? But sometimes you can estimate what is the path, the distance from any node to the destination. For example, if the graph represents like a maze, right? Then you can say, well, like I don't know what the kind of what the length of the shortest path is from here to here. Like it's different between this one and this one. But approximately it's going to be larger if like the distance on the picture between this node and this node is larger, right? So we can approximate the distance to the destination by just looking at like literally like on the picture of the graph, are they far away or not, right? So that's called a heuristic function. So that's an estimate of how far away you are from the destination. The idea with a star is, again, you have this priority queue of nodes to explore. And then the priority is the shortest path from the source to the node in the queue, plus the estimate for how far away the node is from the destination node. So look, and you don't right? So like it's a heuristic, it's an estimate, right? So like if the nodes represent squares on the maze, then you can use the distance as the crow flies as an estimate. And of course, like it doesn't mean anything, right? So like the distance from this to this is like whatever it is, 2 squares, but you can't actually get it all from here to here, right? So it's an estimate, which might be wrong. Yeah. And that's all there is to it, right? So like the difference between Dijkstra and a star is that the priority here is just the shortest path. The priority in a star would be the shortest path plus an estimate for how far the particular node is from the destination.
This is what like this function in C, but then we like write it in Python. You really get much for that.
Say again?
You write a function, if the function says, oh, write this function in C, then we have to write it in Python. Do you get any marks?
No, unless like otherwise specified. Yeah. Question 6. Right. So here, we're saying write a function that takes in starting position and prints out the move from that position that will be that will result in a guaranteed win. Okay. So the idea here is to think about game states as graphs, right? So a game state would be like this, where you could go to 1 or you could go to 2 here. And then from 1, you could go from 1, you can go to 2, and you can go to 3. And from 2, you can go to 3, or you can go to 4, and so on, right?
Just count 1, 2, and 3 numbers.
Say it.
Just count the 1, 2, and 3 numbers. So would
Or yeah. Okay, yeah. Yeah. So this could be like 2 or 3. Okay. So we have this, and then eventually you get to 21 in multiple places, right? So what we want here is we want to explore so we want to explore this graph, and we want to print out the and we want to print out the eventually the path that takes sorry, print out. Sorry, actually, just the move, yeah, that will result in a guaranteed win, right? So okay, so so what does it mean to use depth first search? It just means that, you know, like we first go here, then we go here, then we go here, and so on, rather than exploring kind of using DFS. It does it does say depth, right? Yeah. Okay. So okay. So let's first write the kind of thing that we wrote in ESC180 without considering that we also need the shortest one, right? So this would be like this. So I'll call it like is winning move. And here I'll just say, okay, so if do you win if you're at 21? Yes. So say if position is equal to greater than 21, greater or equal. So like if you are, wait, sorry, so who wins? Is it the one who says 21 first is the winner? So if your position is already more than 21, we'll say you're at false. I need to comment this out. And then here we'll say if it's not a winning position for any of the possible moves, then you are winning, right? So I'll have like moves as 1, 2, 3, and if your opponent is losing, then you're winning. So we'll try every possible move. If not, then it's return false. So this is in fact depth first search, right? So it's depth first search because you go from 0 to 1 so you go kind of depth first, right? As you explore, because like 0 is going to call 1, and then right away 1 is going to call 2, and 2 is going to call 3, so on. So all right. So that is fine, but that does not actually gives you this. So I guess technically the question, like you could imagine a situation where it wouldn't be the case that you need just the largest move. Like in practice here, of course, like the largest one that leads to you still winning is obviously the right thing. So it would be legitimate to just say, okay, so rather than do this, you would just say, you would just try the largest one first. And then that would mean, so the function would be they just start by trying 3 first, and then if the largest one wins, then you don't need to check the smaller ones. And I guess that's kind of enough here. To just return the largest one. That's, so that's just because like it needs to be the shortest path. So, and like obviously the shortest path to victory that still leads you to victory is the one that corresponds to jumping more rather than less, right? So you just try 3 first, and if 3 leads to you winning, then like obviously that's winning. So you could also modify it, I guess. And in addition to this, you can also return the number. You can also return the number of moves that are needed to win, right? So if you're not winning, then you'll return like false. And I guess 0. And now so something so winning the moves. So so something like this. And and then here, so if the opponent doesn't win, then you return like the number of moves for this was this much. If not,
Why do you flow?
it's just because like that's the way to do infinity. So something like this, so that would give you like the number of moves as well. Uh, so it's that you are making one more move. So it's like the number of moves from here and then plus one, which is like the move that you're making. Okay.